Okay, in order to tell you how actually this method works, I want to show you that you know indeed how it works without knowing that you know it. The thing is, as I said, this algorithm or set of algorithms, they work very, very intuitively. And I'm going to use this very simple example. So this simple example, it has two predictors, predictor 1 and predictor 2. So you can imagine that the data set is like predictor 1, predictor 2, and then it has a target. And the target is basically has three different values, A, B, and C. To make it more tangible, let's say that this predictor 1 is daily, the number of daily transactions. And this predictor 2 is the average transaction value or price. And the target variable is whether someone is high risk, medium risk, or low risk for the bank. Okay, you can think about such examples yourself. But I rather go for the abstract version to talk about predictor 1, predictor 2, and the target. We learned that our method tries to understand the association between the predictors and the target. So let's say that this is our training data. And we tell the method, go and learn such association. The method tells us that say no more fam. I got you, and let me think about this association. The method tries to find the subspaces. So this is a space, right? There are two dimensions. This is dimension 1 and dimension 2. So if we have more predictors, we would have more dimensions. And this is called the space, or better to say feature space. These predictors are the features, so we can call it feature space, we can call it predictor space. The algorithm tries to find subspaces, part of the regions of this space, in which it is easier to guess the target value. In the whole space, if the algorithm wants to predict the target value for a new observation, let's say the observation is here, then the algorithm might say that, let's say that 30% or 30% of our points are green, 30% are blue, and 40% are red. So for a new one, our method would say that the chance that it is from the value A, it is 40%. And then the chance for value B is 30% and for C is 30%. So the chance of 40% is not a high chance. Okay? It might go in any direction. It's on the verge. So the values in the original space, they are very widely spread. Okay, they are almost equally spread over A, B, and C. The algorithm tries to find regions that they are more pure. So how to do so? If you draw a line on predictor 2 equal to 250, then you would have a region here that all the values are from target A, target equal to A. So if a new case is located here in this region, with 100%, we can guess with very high accuracy that this new observation has a target equal to a value. Okay? And then the algorithm does not stop here. The algorithm goes and finds other regions. So if the algorithm draws this line that is from predictor 150, then on this region we have more purity. Okay, so it is about purity. We want to increase purity or decrease impurity. The algorithm decrease in purity. The method tries to find regions in which the purity of the target values is higher, or similarly the impurity is lower, even though in the whole space the purity was quite low. And the purity, we can look at it from these values. It is mix of all target values. In the three regions that the algorithm has found, so let me color code these regions. Or better to, let me color code them. In these regions, the purity is very, very high. Let's call this one region 1, and the reason is we found it first, and these two were found simultaneously. So when we draw this line, when the algorithm found this line, then region 2 and region 3 appear together. This process can be shown in a tree-like diagram. And how is it? It is like one space at the start. And the space at the start, the target variables were 40%, so A, 30% B, 30% C. Then the algorithm figures out that there is a very good line, a splitting line on P2 equal to 250. Okay, so if the targets, if P2, is lower than 250, then you are in region 1. So this is R1, right? You are in the region 1. And in the region 1, the distribution of the target is 100% A, 0% B, 0% C. So it is a gold purity. Perfect. But what if the P2 is greater than 250? We would be in this part of the space, right? It is said that, okay, let's look at something else. Let's look at P1. If P1 is lower than 250, so this is 250, if P1 now is lower than 250, then we are, so it is better to, let me do it in this way. So if P1 is lower than 250, okay, so P2 more than 250 and P1 is lower than 250, then we are in region 2 with the purity of 0%, 100%, or the distribution and 0%. And simultaneously, we would have region 3 for P1 greater than 250. And here, the distribution would be 0%, 0%, and 100%. The thing is, purity would be measured by some indices like Shannon's entropy or Gini impurity. But we don't want to learn them because we don't need them. Okay? So just the concept is important, concept of purity. And this is why we call the method a decision tree, because it's like a tree, but it's upside down. So this is the root, and this is the branch. And this is called node or leaf. And this is leaf. And this is leaf. Okay? Indeed, these are terminal nodes. These are terminal nodes. Because the tree is terminated. There is no branching anymore. So, to wrap it up, the method tries to find subspaces, the region inside, the small little regions inside the space of the features, in which the purity of the target is higher. And why? Because when the purity is higher, we are more confident in our guess comparing to the situation when the purity is lower. And the purity is high when we have only one type of these categories. Okay? When we have lower spread. So purity and spread of the values over the categories. When the spread is lower, we have higher purity, and vice versa. Okay, so in a more formal way, the algorithm tries to learn the association between predictors and the target, as it learned it outside in the previous slide, that if predictor 1, so this is the associations, if predictor 2 is lower than 250, then target is A. If predictor 2 is higher than 250 and predictor 1 is lower than 250, then target is B. And if predictor 2 is higher than 250 and predictor 1 is higher than 250, both of them, and then the target is C. So this is the association that our method found in the very simple example. So the method tries to learn this association by stratifying or segmentation or splitting the feature space into regions in which the target variable's value is easier to guess. So higher purity. Purity is higher. These regions are called subspaces as well. So regions, subspaces, they are distinct and non-overlapping. Okay, so the space is split into these distinct and non-overlapping regions in which the purity is higher than the initial condition. We explained feature space and predictor space. These are the space that is built by the features or by the predictors. The outcome is a segmentized space shown in a tree-like diagram I showed you intuitively. The higher splits are pointing to more important variables for prediction of the target. So in our case, the first split is based on P2, and it says that P2 is the most important variable in splitting, in finding the more pure subspaces, or in prediction of the target. And then P1 is the second most important variable. So the most important determinant or predictor, the predictor that its values are closely knitted to the target values. And the goal is finding such subspaces in which it is more probable that our educated guess is correct. The target variable has less spread, or better to say that the purity of the target values is higher.